Okay, so we continue with our discussion in section 6.5. All right. Okay, so we have defined the concept of conditionally absolutely continuous random variable given a discrete random variable n. Okay, so and suppose that this function, okay, is a conditional PDF of x given a discrete random variable n. Okay, equal to n equal to d to n. All right. With the probability that capital N equal d to n is positive. Then the probability of the event, okay, x in bracket say A, given that capital N equal to d to n is the integral okay for all Barrea set A in R. Okay. In the definition of conditional PDF, we require only that the identity is true for an arbitrary interval. Okay, so when A is an interval in the real line, but with that, it can be shown that this is also true for any Barrea set A. Okay, and so we also mentioned that if x is a continuous, is a conditionally absolute continuous random variable given a discrete random variable n, okay, then x is absolutely continuous with PDF, okay, and the PDF is that sum over all n such that this probability is positive, so that is This will be times n. Okay. Right, so, and we say that this is an exercise. Okay. Okay. All right, so conditionally absolute continuous random variable, all right, given a discrete random variable n, it is stronger than saying that x is absolutely continuous. Okay, so now, so if x is a continuous, so if x is a conditionally absolute continuous random variable given a discrete random variable n, then we define. So we define the conditional probability of the event x in of the event n equal to little n, given that this absolute continuous random variable x is equal to little x. As okay, so we define to be the all right, divided by okay, okay, if the denominator is positive and this is if okay, where is this PDF? Okay. All right. So now we are able to define such a conditional probability of the event given that this continuous random variable x is equal to little x, like this one. Okay, right, and now we will check. Now, for any Borel set A in R, we have, okay, so now so we now compute this integral. Okay. Okay. Right. Now we do the substitution. Okay. But here, so now this is equal to, all right. So when we do the substitution, oh, okay. Before that, so okay. And now, so this is probability n equal to n, and oh, yeah. So we will divide it into two parts, x in A and of x greater than 0. Okay, so here we have okay, plus oh, by the way, I will say x in A intersect with O y such that greater than 0. Okay. Plus in A intersect with such that it's 0. Okay. And so by definition, this is P of okay, and x of dx. Why? Because that we have things. Okay. And now we can cancel them. Okay, so we can cancel this one. Okay. All right. And so now intersect with and now here is okay. So but okay. And as we so that in this intersection, the marginal density PDF of x is zeros, right? So over there, this is 0, so the integrand is 0. Okay, and so now this parts is equal to 0. Okay, the second integral is 0 here. Okay, and all right, so this is the dx here. This is dx. Okay. And the probability, right? So this is independent of x, so we can move it out. Such that, oh, so this is greater than 0. Okay, and next part. Okay. So now, okay. Now when the probability is greater than 0, so then so 0 is equal to, all right, now, okay. Now for y in R such that fx y 0 x equal to, okay, and that this is for with little n here. Okay. So we have Okay, so we have must be 0 for all n such that probability of is greater than 0. Okay, so we can see, because this is 0, right? And this is positive, okay, because we sum over now, so that this must be 0. Otherwise, if this is not 0 for this particular y, then this product must be positive, and this must be positive. Okay, so we have this one. All right, and so you can see that this implies that if we so that's for n such that probability of is greater positive, we have that the integral a intersect all the y in R such that as y equal to 0, okay, of f, okay, becomes to be intersect of y in R such that f of x 0 dx, so it's 0, because that if x is in here, when this marginal PDF of x at y is 0, which implies that the corresponding value of the conditional PDF must be 0. Okay, when for all n such that this is positive. Okay, and okay, so we can. So now we can add a term. Okay, so we can add a term. A of given is equal to probability of, okay, and x in A intersect y in R greater than 0, okay, plus probability intersect such that equal to 0. All right, because if this is 0, then no matter what you have, the product is 0. Okay, so and if this is non-zero, then as we have shown here, this integral should be 0 because the integrand is 0. Okay, so this term actually is the 0. All right, and we combine these two integrals together. So this is n and x in A. Okay, because that things R is equal to the union of these two subset. Okay. Okay, and now from our previous extension here, right? This integral is equal to this conditional probability. Okay, so this is the x in A given, right? All right, so this is the conditional probability of this event given the event that n equal to n. Okay. All right, and so that this is just the joint probability. Okay. Okay. So we have shown that the joint probability, okay, is the integral of this conditional probability of this event given capital X equal to little x, okay, multiple times with the marginal PDF of random variable x here. Okay, so now we have achieved our goal, right? Okay, so we have a proper definition of this conditional probability of the event capital N equal to little n, given that this continuous random variable x is equal to little x. Okay, with this definition, then we reach to the identity we want here. Okay, so we want here. Okay, and so we now summarize the previous discussion in proposition I. So proposition I here. 6.5.I. All right, so let n be a discrete random variable, and x an absolutely continuous random variable. Okay, so we have two random variables. One x discrete, the other is absolutely continuous. Then x is conditionally absolutely continuous given the discrete random variable n, if and only if, okay, if and only if, right? So we know conditional absolute continuity is stronger than absolute continuity. Okay. So if and only if for each n in R, there exists and this non-negative and and the integrable function P of x in R such that the joint probability can be computed by the product of this function of x and for any Borel, oh, okay, I forgot, with a PDF of x, okay, and for any Borel set A in R. And furthermore, we have the identity equal to for all n x for almost all x in R and for all n in R. Okay. Okay. So this proposition provides an answer to our question we raised up in the previous class lecture. Okay. So that so that the concept of conditionally absolute continuity will be important in the expression of this proposition. Okay. And if we look at the previous discussion here, the previous discussion give us the forward direction. Okay, so if x is continuously is conditionally absolutely continuous, given the discrete random variable, and then we have shown that we can construct a function of x, right? So we can construct that for each n little n. See here, for each little n in R, all right. So for each little n in R, that we define a function. Okay. So if little n is given here, now this becomes to a function of x. So I can give a remark here. So given, so fix n in R, okay, is non-negative and integrable. And non-integrable function of x in R. Okay, so we have defined this one. Okay, we have defined this one, and we have shown that through the development here that okay, this joint probability is equal to this integral here, right? This integral here. Okay, so that the forward direction is already in the previous discussion. And the identity here. So look at identity. So now in here, so you can see that for every little n, okay, and if for every little n here, okay, for x such that this is positive, then by definition we can move to here, right? So that this function times the PDF here is equal to this one, okay? Is equal to this one, and when this is 0, okay, when this one is 0, okay, then when we multiply, so when this marginal so the PDF of capital X is 0, of course this product is 0, okay? This is 0. And we see that from the discussion that when this is non-zero, then the conditional PDF at this X also 0. So the product is 0. So we have, and if this is 0, of course this is 0 already, right? So this identity is always true, okay? Always true. But the reason why I put almost all X is because that when we define this function, the PDF of X taken here, this summation here, okay? But as we know, this summation, this PDF is one of the PDF of the random variable X, and but this one, okay, it may be another PDF of X, right? Because in here we are given a PDF. So this PDF, all right, this PDF may be different from this one, but they are equal for almost all X in R, as we have shown before. So that so if we replace, all right, this one by a version of a PDF of X, then that the equality should be for almost all X in R. Okay, so that is the reason why I put here. All right, so to allow us the degree of freedom that we can choose an arbitrary PDF here, okay, in the proposition. Okay, so we demonstrate that this must be true already, okay, from the definition. All right. Okay. And so well, so a proof of this proposition proof. So the direction this has been done, all right, in the previous discussion. So we have done, okay, and now the backward direction. Okay, so the backward direction. So now for each little n, there exists, all right, a function, okay, a function like this one, such as this is true. Okay, this is true. All right, and so we have to show that x is conditionally absolutely continuous given the discrete random variable n. All right. Okay, so right. So now for n in R, okay, so we consider such that the probability of this event is positive. Okay, so we have, okay, the probability that x is in I, okay, given this event, okay, and which is the divided by, okay, right. So this is from the definition of conditional probability of an event given another event in chapter 3. Okay. Now the numerator is a type, right, of this joint probability. So now we can use this, all right. So this becomes 2. Probability x equal to little n and the x here. Okay, so we have this function, right? And it's that. Now, so we can and dx here. Okay, now we know oh, yeah, so okay, where, so we define okay, to be this ratio. Okay. So we find a function for every interval. Okay. So we find a function here. So this is for all x in R. Okay. So for any n such that this is positive, then this conditional probability of the event x in I, given the event capital N is equal to little n, can be evaluated by this integral. Okay, and the integrand is defined in here, which is where x, as we know, which is non-negative, and integrable. Okay. On R. Okay. All right. So thus x is conditionally absolutely continuous given the discrete random variable n. Okay, so we complete the proof of the backward direction, and finally, that the identity right? The identity in the statement of the proposition has been done in the previous discussion. Okay, so we have done. Okay, so so we complete the theoretical study of mixed type of the conditional distribution. All right, about mixed type, about random variable of different types. Okay. Okay. So let me give an example from the textbook. This is, I think, this is example 6.5.d in the textbook. So they are n plus m trials right? All right. There are in-person trials, and with each with a common probability of success P. Right. So a trial, and either we have a success or we have a failure, and so the success probability will be P. Okay, and the success probability P is not fixed, okay, in advance. Okay, but is chosen from a uniform uniform 0-1 population. Okay. So which means that P, the success probability itself, is a random variable and has uniform distribution, okay, over the interval from 0 to 1. Okay. So now we ask, what is the conditional distribution, okay, of the success probability P, given that the n plus m trials, right? The n plus m trials result in n success. Okay, so this is our question. Okay. All right, so we let x be uniformly distributed random variable on this open interval, and we let n be the number, okay, of success in n plus m trials. Okay, so you can see that x is an absolute continuous random variable, and the n is a discrete random variable. Okay, and taking values from 0 to n plus m. Okay. Right? Okay, and So that we want to show that x is conditionally absolutely continuous. So we want to show that x is conditionally absolutely continuous given the discrete random variable n, right? By establishing conditional okay, by establishing a conditional PDF okay of x okay given that n equal to n with the probability of I think because n has been used there, so I use k. All right, greater than 0. Okay, so this is my purpose. Okay, so you want to know. Okay, so we have, if we can establish a conditional PDF, then this conditional PDF will be conditional distribution, right, of the success probability, which is modeled by a random variable x here. Okay, a random variable x. Okay, and given that the equal to k into k. Yeah. Okay, so now, okay, now we can, so look at the proposition 6.5.I. It shows that to justify the x is conditionally absolute continuous given a discrete random variable, and if we can, right, if we can construct, okay, for each n, okay, which n, that a function, okay, a function of x and has this property, okay, so that we need to do that. Now, how to construct them? Okay, so the conditional, all right, distribution, okay, so the conditional probability mass function of n given that x equal to little p is here. Okay. Okay. So we know that the k, so we have here that if k is in between 0 and n plus m, then we know, okay, so because the trial are independent, right, so that we have k plus success, but we have m plus m minus k failure. Okay, for 0 m, right? And we know this is 0 otherwise. Okay. Okay. So that we have this case here. Okay. So you can see this is so it's a function, so that which is a function of p. Y is a function of p for each k in R. Okay. For example, if k is an integer between 0 and m plus m, okay, and okay, oh, there must be an integer, but if k is not an integer between 0 and m plus m, then the function is the 0 function. Okay, all right. So you can see a 0 function, and but if k is an integer between 0 and m plus m, now you can see that this is a polynomial function of p. Okay, so it's a polynomial function of p. You can see. Okay, all right. So we have established the function already. Okay, and then but we have to justify. We have to justify this identity. Okay, we justify this identity. Right, and we have so that the probability of n equal to k and x in A oh, by the way, so we have now okay. All right. So if this is true, that okay. Oh, I think just right here, just for case, and for k in Z and k is in between n plus m. Okay. If we do the integration, okay, so we just check that the probability n equal to k, x equal to p, okay, and the fxp dp, okay, and p in the interval, okay, in an interval here. So that and p is the interval intersect 0 and 1, okay, because that x is uniformly distributed from the value on 0 and 1, okay. So this is the p equal to p, all right, and dp, okay, over, because the density in here, so that is equal to 1 when p and 0 otherwise. Okay, so we know that because it is uniform distribution. So it is okay. So this is 1 when p is in the interval. So that we will see that. So this integral over the intersection of the interval I and this open interval 0 and 1. Okay. And for this one, it is easy. So we can put and the k here. Okay, and pk 1 minus p m plus m minus k and the dp. Okay, so this is the integration we have here. All right, and so that n equal to n. Okay. Oh. Okay. Oh, I see. So I think we will I will create. Okay. So I think I will create it directly. Because that from the okay, I think this is the far away. Okay, so here I think we can directly construct. All right, the conditional PDF of random variable x given n when this probability is positive. Okay, so, right. Okay. So now, right. So by proposition 6.5.I, okay, for n in R, such that, okay, so for k in Z, such that k is in between 0 and n plus m, okay, that f we define, okay, P of k, okay, to be n equal to k, and x equal to p, f xp, okay, and the probability. Okay, right, great. Okay, so we establish, okay, this function. Okay, so we establish this function here, and we already have this one, right? Defined here. So we know the conditional PMF or the conditional distribution of n here. And we also know that the PDF of a random variable x is uniform over 0 and 1. But we don't know this, right? We don't know this one. Okay. This is how to compute, right? So that, so we know this is equal to a constant, okay, something, right? This is also a constant, right? And probability of k, right? And this is 1 minus p, n plus m minus k. And this constant depends on k, so I will, the constant of k, okay, and p to the k's power, 1 minus p, n plus m minus k, right? And this is, and we know this is true for, right, and also 0 otherwise. Okay. Okay. So we have that. And we know this function should be as the property as a PDF of an absolute continuous random variable. Okay. All right, and we see, of course, this is a non-negative, of course, a non-negative and integrable function. And what is this constant? Okay, and now to have to be a conditional PDF x given that n equal to k, right? With k, all right? Right. We must have one, okay, right, must be equal to 1. So the overall integration should be 1. And so this is ck, right, and from 0 to 1, p to the kth power, 1 minus p, m plus m minus k. Okay? Right, so this is integral. All right, so this implies that this constant, right, this constant x1 over the integral minus k here. And we know this is the beta function. Okay, so this is b of k plus 1 and n plus m minus k plus 1. Okay, so this is the beta function we have discussed in chapter 5. Okay, so this is the beta function. All right, so that's, we have that f k is equal to oh, by the way, sorry. Okay, I'm sorry. This integral is the beta definition of beta function, and m plus m minus k plus 1. Okay, I'm sorry. So the integral is the beta function of k plus 1 and m plus m minus k plus 1. Okay. All right. And so that's okay. So now, so by the substitution, so we have k m plus m minus k plus 1. Okay, k minus k, and the 0 otherwise. Okay, so we have this is the distribution here. All right, so you can see that which is a beta. So it's a beta distribution. And in particular, with k equal to n, okay, so we want, given the success n, right, then fx p given it to n becomes 2 1 over p n plus 1 and m plus 1 pm minus p pn minus pm and the 0 otherwise. Okay. Right. Okay. So we will omit section 6.6 on order statistics. Okay. So now we will go to the last 6.7. We want to discuss the joint probability distribution of several functions of random variables. Okay. And interval QQ, we will consider functions of jointly absolutely continuous random variables. Before that, I would like to define open set in the n-dimensional Euclidean space. Right, so a subset U of Rn, okay, is called open if for all point x in U, there exists an open ball. Okay, so the open ball is here. Such that the center is here and the radius is R. Okay, so there exists an open ball with center x and radius R greater than 0. So there exists such that this open ball is contained in U. Okay. So U is an, so suppose we have, this is U. So U is an open ball. If for every point x in U, we can find an open ball with a center x and a radius R, which is positive, such that the open ball itself is contained in U. Okay, so it's called the open set. Right. Now we let x1, x2 up to xn be jointly absolutely continuous random variables. Okay. And we let U, right, be an open set, okay, in Rn, which contain the range, right, of the random vector. Okay, the random vector formed by these n random variables, i.e., the range of xn would be x1 omega, x2 omega, xn omega in Rn for all outcome in the sample space were contained in U. Okay? So this is the range of the vector function. Okay? This is the ranges here. Because for each outcome, well, we have a point in Rn, okay? And when we run over all possible outcome in the sample space, then we obtain the range of this random vector, okay? And this random should be in U, okay? Okay, and now consider n piecewise continuous real value functions g sub I of x1, x2 up to xn, okay, defined on U for I from 1 to n. Okay, so we consider n piecewise continuous real value functions on U. Okay, and for I from 1 to n, we let capital Iy to be the a function of these n random variables. Okay, so that x goes to Rn. Okay, so that goes to U, and goes to R. Okay, and this is x1, x2, and this is g sub I. Okay, this is g sub I. So each g sub I is defined on the open set U. Okay, depending on open set U. Okay, so that, and as we know, the open set U will contain a range of this random vector. So this is a vector mapping, right? So for H omega, we'll go to x1, omega, x2. Okay, and then goes to gi, x1. Okay. All right, so y sub I is the composition of these two functions. Okay, so y sub I, again, and so by proposition, I think the proposition in chapter 5, I think so. Is that correct? No. Oh, no. Okay, so proposition, I think, is in 6.1. Let me see. A, I think so. That y sub I is a random variable. Okay. Yeah. Okay. So this is a random variable. Okay. Now, so our question is that are y1, y2 up to yn jointly absolutely continuous. Okay? And if the answer is yes, okay, how do we find a joint PDF for name? Okay, so both are natural questions to raise up, right? Okay. All right, so we will try to answer this question. Okay. And we will see that the answer of this question depends on the functions we have, okay? The G sub I. Okay. Okay. All right. So now we will first of all we consider a vector function formed by n scalar functions, right? Called the coordinate transformation. Okay, so now let U, okay, be an open set. All right, so be an open subset of Rn. Okay. A vector valued. So a vector valued function G, okay, with n component defined on the open set U, and the codomain is the n-dimensional Euclidean space. So U is a subset of Rn, and this vector value function is Okay, from there. All right, so a vector value function, okay, which has n components, is called a coordinate transform. Right, so it's called a coordinate transformation. On the open set U, if it has the following three properties. Okay, so I will list the three properties. First, the vector function G is continuously differentiable. Okay, on U, which means that the first order partial derivative okay, so it's Gi xj exist, okay, right, for all x in U, okay, so all first order partial derivative, this is the first order partial derivative, because each G sub I is a function of n variables, so this is the partial derivative, and exists for all points x in U, okay, and is continuous, and the partial derivative is continuous. Okay, it's continuous on U. Okay, for all ij from 1 to n. Okay, all right. So first of all, we require that this vector value function is continuously differentiable on the open set U. Okay. The second property is that the G itself, okay, is 1 to 1, right? And onto. Okay. Oh, by the way, just 1 to 1, okay? 1 to 1 on U. Okay. Okay, so it's 1 to 1 U. And third one, the Jacobian determinant, okay, denoted by J here at the point X, which is defined to be the determinant of the matrix formed by the first order partial derivatives. So this is here. For the first row consists of first order partial derivative of G1. Okay. And the second row corresponding to all first order partial derivative of G2. Okay, and the last row corresponding to all first order derivative of Gn. Okay, so this determinant is called the Jacobian determinant. And the Jacobian determinant, all right, is non-zero. Should be non-zero for every point x, all right, in the domain, in the open set U. Okay. All right. So that we have, so if a vector value function on an open set is called a coordinate transformation on the open set U, if it satisfies these three properties, okay, it satisfies. Okay, so there is a remark. All right. About the third property and other three properties. The first one is that since the Jacobian determinant, okay, and you see that Jacobian determinant actually is a scalar function of n variables. Okay, so it's a scalar function. So think the Jacobian is a continuous non-zero, so number 0, right? Real valued function on the open set U. It must be a positive or negative function on each connected component of D. All right, so this is the so for example, right? So we let G1 xy to be the ratio here, and G2 xy to be y itself. Okay. Right. Then you can see the first function is undefined when y equals to 0. Okay, so that So we should find an open set such that G1 and G2, right, are defined, okay, on that open set. So we let U to be all the point in R2 such that Y is not equal to 0. And of course, it's an open set, so that it can be decomposed into two half plane, such that Y is positive, disjoint union with Y is negative. So we will say D plus, disjoint union, D minus. Okay? All right, so this is here. Look at that. So that this line, the x-axis, is corresponding to Y equals 0, right? And so we have decomposed so that this upper half plane is D plus. And the lower plane is D minus. And you can see D plus is a connected component, right? Because any 2 points in D plus can be connected by polygon. Also, again, D minus is also a connected component. Okay, so that in here we see that okay, so we know D plus and D minus are two connected components in U. Okay. Okay, so that's we define G to be G1 and G2. And this function is from U to R2, right? It's U from to R2. Okay. And so now we check, first of all, that G1 of X, okay. So the partial derivative would be 1 over Y, okay. And dy minus Y squared X and G2, which is 0, and G2, which is equal to 1. Okay. So you can see that are continuous on U. Okay, so you can see these four first order partial derivatives are continuous, so that thus G is continuously differentiable. Okay, on U. And second, to show that it's 1-to-1 and it's 1-to-1, we will find the inverse of this G. Okay, so now we let Z to be G1 XY and the W to be G2 XY. Right. And from that, then, okay. So we know this is X divided by Y, and W to be G2 xy, which is y. Then we see that x is equal to z times w, right? Because when z times w, you get x. All right, and this is called h1 of zw defined. Okay, and y is just equal to w. Okay, y is equal to w, so this is called zw. Okay, here. All right, and from there, you can see that w never a 0, okay, but z can be any real numbers, okay, can be real numbers. So you see that, you can see that the range, the GU is equal to U is again. Okay, so you can see, and the H1, H2 becomes to be, all right. So that then, and the H1, H2, which is from U, goes to R2. Right? It's a vector function. And we will see that G compose H compose G x y. Okay, so this is H of G1 xy, G2 xy. Okay, and this is equal to H of y and y here. Okay, and this is become 2H1 of x, H2. All right. Okay, and H1 is the multiplication of Z and W, right? So when we multiply them together, we get X here, and this is just Y. Okay. Okay. For all X, Y in U. And similarly, G, H of ZW. So this is G of H1 ZW, H2 ZW. So this is G of G times W and the W. Okay. And this is G1 ZW, W, and the G2 ZW, W. And by definition of G, okay, the ratio here is ZW divided by W, and the G2 is just the second argument, and so this is ZW. Okay. So which shows that H is the inverse okay. So maybe I give you the U here. So is the inverse function of G. Right? So that G is 1-to-1 on U. Okay? Okay, so we proved that this vector function G is 1-to-1 by establishing the inverse function of G. Okay. Now the third one, the Jacobian. And the Jacobian is here, so we know okay, this is our Jacobian, and this is 1/y. Okay, and which is non-zero for all x, y in U. Okay, because in U y cannot be 0, so this is 0. And also in D1, D plus, and also the Jacobian determinant, all right, which is positive for all the points in D plus, because in D plus the y is positive, and the Jacobian is negative for all the points in D minus. Okay, so you can see that the Jacobian, because the Jacobian determinant is non-zero, right, as required for every point, so that it is either positive or negative in each connected component, all right, D plus or D minus. So that we have demonstrated that here. Okay, so this is about the first remark. And the second remark here is that okay, from 1 and 3, the first property say that the vector value function G is continuously differentiable, and the third property says that the Jacobian determinant is non-zero for every point. Okay, and of course the Jacobian determinant must be a continuous function, right? Because every first order partial derivatives is a continuous function of n variables. So from this one, that the vector value function is an open mapping. i.e. G, V right is an open subset. All right, so the G of V, so the value, right, of the vector value function on V is an open subset of Rn for all open subset V, okay, contained in U. Okay, this property is saying that G is an open mapping. So you will map open set to open set. Okay, so V is an open set and goes to here and GV. Okay. So open mapping says that GV is an open set. Then V is open set, and GV is also an open set. Okay. Okay. It's called open set. In particular, G U is the range of G, because the domain is U. It's an open set. Okay. All right. So this is about the discussion of coordinate transformations. Okay. So that. Okay. So now, from property 2, the vector value function from U to its range. Okay. Right. So if the codomain is restricted to its range, then this is 1-to-1 and onto. Okay. So it's 1-to-1 and onto. So this function G, this vector value function, will be on 1-to-1 and onto, so that it has inverse. So its inverse function, all right, H, which is from the range to, so from the range to U. Okay. Right. So the vector value function is 1-to-1 and onto, so that it, from the theory of function, we know it has inverse. So its inverse is here. Okay. So its inverse is also, okay, a coordinate transformation on GU. And by the and by using the chain rule, okay, by using the chain rule, that so we have two matrices, okay. They are called Jacobian matrices. Okay, so where the y is the vector values of G at the point X. Okay, so y is here, and the I okay, is the n times n identity matrix. Okay, and the differential are, so these two are Jacobian matrices of the vector value function H and the vector value function G at Y and at X respectively. Okay. And note that the Jacobian matrix, all right, so let me see that is the matrix containing all first order partial derivatives. 1, okay, that. Okay, so this is the Jacobian matrix of the vector function H. And the D of G, the Jacobian matrix of the vector value function G at the point X. All right. Okay, so so we know that the multiplication of these two Jacobian matrices will becomes to be the identity matrix. Okay, and you have to know that the Y is the vector value of G at the point X here. Okay, so this is we have the relationship, right? And this is from the chain rule, okay, from the chain rule. So we know that whenever that 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 G, the vector value G is 1-to-1 and onto, and we know G is continuous differentiable, right? So we can apply chain rule to show that the inverse function H is also continuous differentiable. Okay, and of course it's 1-to-1, right? Of course it's 1-to-1, and the Jacobian the determinants, right, which is just the determinants of the Jacobian matrix. And we know when we have this identity, we take the determinants. So from the determinant formula of linear algebra, that the determinant of this matrix times the determinant of the matrix is equal to the determinant of the identity. But we know the determinant of identity is equal to 1. All right, equal to 1. So when the Jacobian determinants of G is non-zero, of course, the Jacobian determinants of H is also non-zero. Okay, so it's quite easy to see that the inverse function H of the vector value function G is also a coordinate transformation. Okay. So the remark that I checked some here is that so since the Jacobian determinants of G is the determinant of the Jacobian matrix. Okay, so this is the notation of determinants, and is equal to so we have that the Jacobian times the Jacobian is equal to 1, okay, for all x in U, where y is just equal to g of x. Okay. All right, and the usage of coordinate transformation is to give us a change of variable formula. So now we next state the formula, okay, for the change of variables through coordinate transformation. Okay, and I just stated in the following proposition. Okay, so let U be an open subset of Rn, and let G be a coordinate transformation on This opens U. Now let f be a real valued function, okay, defined on the image G D G U of G. Okay, or the range, that's fine. Image or range of so the range, right? Okay, and assume the integral over GD f of y. Okay, so f is a real value function defined on the range, right? And so if we integrate over the integral of the function over this range, so if the integral exists, okay, assume that then the integral, okay, u, oh, G, u, f of g of x and the Jacobian of x, but we take the absolute value and the dx also exist. And so if this integral exists, then this integral exists, and they are equal. And this is equal to okay. So we have do the change of variable. So the here we use y to be gx. Okay, we use y to be gx. Okay, as the change of variables. Okay, so you can see that the y, okay, which is an n vector, right, an n vector point. All right, and so the variables y1, y2 up to yn has been changed as a function of n variable x1, x2, xn, okay, but according to a coordinate transformation G here. Okay, so that the differential n-dimensional volume here, okay, is actually the absolute value of the Jacobian of this coordinate transformation at the point here with now another differential, the n-dimensional differential volume here. Okay, so you can see that the dy here has been replaced by this one, and we change the variable y to be the vector value function G. And the integration here, instead of integrate over the range of G, when the variable is Y variables, when we change to the X variables, then with the integration is over the open set U itself. So this is basically, this proposition is the change of variable through coordinate transformation. Okay. Okay. So this is an extension from one-dimensional to n-dimensional. Okay. Because and I believe that you know. Okay, this concept. Okay, and I think I will supply a reference to, if you are interested in the proof of this proposition, then so the proof, please see section 15.9 on pages 416 to 421 in TM Apostle textbook called Mathematical Analysis. Second edition, 1974. All right. So if you are interested, you can look for the contents in this section, right, of this textbook by T.M. Apostle. Okay. Okay. So a remark is here. The integral identity in above. So the integral identity means this integral identity. Okay. Proposition is still valid over any Borel on any Borel set. Of Borel subset of the U here. Okay. Now, once we have the change of variable formula here, okay, then we will be able to answer our question partially. So the next proposition, okay, give a partial answer to our questions raised at the beginning of this section. Okay, so let me state it. Proposition 6.7.b. All right, so we let x1, x2, xn be jointly, absolutely continuous random variables with a joint PDF, which is x1, x2, xn of x1, x2, xn, and such that this joint PDF such that is equal to 0 almost everywhere outside an open set by an open subset. Okay, an open subset U of Rn, which means that if we integrate over the complement of U, right? U is an open subset and the complement, and we integrate is equal to 0. Okay. And as we know, this integral is actually the probability that the random vector is in the complement of this open set. Okay. Okay. Another word, so this is 0, which just saying that the probability that the random vector takes values in U with probability 1. Okay? Right, so this is, which means that the vector function, the random vector here, has value in U with probability 1. So of course, the random vector may have value outside of the open set U, but the probability, the total probability is 0. Okay, it's 0. So that is the statement here. Okay. So this is first is about the joint PDF. All right. So we describe the behavior of the joint PDF of this unjointly absolute continuous random variables. This is about that. Okay. And now we let the vector function G so let this vector function be a coordinate transformation on U. Okay, So we let this one. And then we let H be, so this is from G, U to U. Okay, be the inverse transformation of G on GD, GU. Okay, so we know the inverse, this inverse function is also a coordinate transformation, as we discussed before. Okay. All right, then y1, which is g1 of x1, y2, which is g2, and yn, which is gn of x1, x2, are also jointly absolute continuous. All right, also random variable with a joint PDF. Okay. Okay, so the joint PDF becomes to be, so we can times the Jacobian determinants of the inverse transformation H. Okay. And as we know, the Jacobian of the inverse transformation H, okay, times the Jacobian of G is equal to 1. All right, so we have divided by Jacobian of G okay, so you can see that they are here, but the expression is in terms of the point G, but we want it is in terms of point Y, so that we have to use the H function and G of H okay, the absolute value here. Okay. And so this is true for all points in G in the range of G. Okay. And the joint PDF is 0 for all y1, y2, yn, right? Not in GU. Okay, so I think I use this one. Okay, so the statement is like this one. Okay, so if the functions of the function G1, G2 up to Gn, these n functions together, if this n functions together form a coordinate transformation, then by this n data processing on the n random variable x1 up to xn to create n new random variable y1, y2 up to yn, then this new random variable will also jointly be absolute continuous random variables. And then we can find a joint PDF for this new random variable here. And we can see that, all right, it can be obtained by using the original joint PDF of the old random variables here, and also the Jacobian, all right, determinants of the coordinate transformation G. Okay, but we need to use the inverse transformation H, right, to obtain the x point from the y points. Okay, yeah, because in here x point and y point, they are this is a one-to-one correspondence when the points is when the x point is in U here. Okay, so we can have a PDF such that it is also concentrate on the GU here, and then we can assign 0 values for this joint PDF whenever the y points is not in the range of G. Okay, so this is give us, okay, the answer. And the proof actually follow directly from the range of variable formula, okay, as we will see. Okay, so for convenience, we let random vector x to be x1, x2 up to xn, and random vector capital Y with y1, y2 up to yn. All right, and the n vector x is x1, x2, up to xn. Y, vector y would be y1, y2 up to yn. Okay. Now, since it's 0. Almost everywhere outside D. Okay, so we know that this join the PMF of the x random variables. Okay, so this is actually the same as this one, but we use a vector notation to write it. All right, so since this 0 almost everywhere outside D, so we have here that the probability that the random vector is in U is 1. Okay, it's in 1 here, as we have just computed here. And then the probability that random vector y in G U and we know random vector y is the vector function of random vector x here in G of U. And but because G is 1 to 1, okay? Because G is 1 to 1 here, so that this is equal to x is in U. Okay? Since G is 1 to 1 on U. Okay. And so this is 1 here. Right. So we see that the random vector y is concentrated on this open set G of U. Okay. So that we will focus on we will focus on this open set, right? On this open set here. All right, now, so we let Q of y. Okay, so for each y point, we see that. So this is the N cell. Okay. Okay, so you can see this is an N cell. Then we have that. Now we look at the join CDF of the y random variables. And we know that this is the probability that the random vector is in this N cell. Okay, by our definition. Okay, so this is, as we know, this is just the probability that y1, right, less than equal to y1, y2 less than equal to y2, yn less than equal to yn. Okay, so it's the probability of this joint event. And by using the random vector, this is just equal to, okay, so n cell. So the random vector is in the n cell. Okay, the n cell. Okay, and we can intersect with the range of G. They are equal. Why? Because we have just shown that this event occurs with probability 1. Okay? So this event occurs with probability 1. And so that when you intersect with event, okay, maybe I will say that y is in GU, okay, and plus probability of y in QY, and y in the complement of GU. Okay. Because y is either in G of U or outside of G of U, right? So we have the composition. But the probability here, so this probability, look at this probability. This probability is less than or equal to the probability that y in GU complement. But it's 0, okay? Because that this event has probability 1. So that the probability that random vector y is outside of the G of U should be 0. And so this probability is less than equal to 0. So this must be 0. Okay, must be 0. And so that this is probability of y in QY intersect GU. Okay. Okay. So this is the, in terms of the, because and then this is probability that G of X in Q Y intersect G of U. Yeah, because Y is equal to G of X here. Now, we apply the inverse transformation on both sides. So this GX is in H of QY intersect here. Okay, because since G is 1 to 1. Okay, then onto I think just one way so is enough. So this is the probability that X, because H is the inverse transformation of G on U, so that the random vector X is in the H of Q Y intersect G of U. Okay, right, and so that this is the integral of over the point of H and the QY intersect GU. Okay, and by using the joint PDF of random vector X, okay, over this set. Okay. And now we use the change of variable. So we so that by letting by the change of variables, okay, which saying that X is equal to HY. Okay. All right, and so that then Y, it will be in QY intersect G of U. Okay, and we have H of X and H of Y right here, and the Jacobian of H of Y, and the absolute value of the Jacobian determinants of dy here. Okay, so this implies that dx is the Jacobian of this vector function, and take the absolute value and dy. Okay, so this is by the change of variable. So we have that. This is the case here. Okay, so we here use the proposition 6.7.8 here. Okay, and so that we will have y in qy and f of y. Okay, so now we express over this n cell that integrants here, and where so where defined to be that f okay, this one if y is in GU, and 0 if y not in GU. Okay, so this 0, right? So so that the intersection is here. Okay, right. So when y is in QY intersect with the complement of GU, then this function is 0. Okay, by definition. Okay, so that okay, so the joint CDF of y1 up to yn, right, can be expressed by this way. So you can see this is the so this is the integration of y1 yep, okay. So if you want to integrate, oh, oh, okay. I think because y has been used, so I have to use z. Okay, z here. Z here. Okay. So I'm sorry. Z. Okay. Because y has been used. So for all the points z in this set. Okay. So this is z. Okay. And z here. Z here. Okay. All right. And the evaluation, as we know, so this is for y1, y2, yn here, and f z1, z2, zn, that's d of z1, dz2, dzn. Okay? So from this expression, we know this is indeed a joint PDF. Okay? Right. So this definition. Okay. Now you can use lit y instead of the little z here. Okay, it's fine. Okay. Okay, so this shows that y1, y2 up to yn x jointly absolutely continuous with a PDF, with a joint PDF. In above. Okay? So we have that. And note that the expression here, they are also the same. This is actually okay, So you can see they are equal, this expression and this one. Okay. So that this is okay. So that this is the expression of this one, the same. Okay. So we complete the proof. Okay, so this is a proof here. And the final stage here is that, so we next state an extension of proposition 6.7.b, okay, for transformations which can be segmented into pieces of coordinate transformation. Okay. All right, so let x1, x2, xn be jointly absolutely continuous random variables with a joint PDF f x1 okay, such that this joint PDF is 0 almost everywhere. So almost everywhere. Okay, outside an open subset U of Rn, i.e. the probability that the random vectors in U is probability 1, where the random vector is denoted in this way. Okay, so that we have so that this is concentrate in the open state. Okay. And now let a vector value function okay, so be a vector valued function on U, on this open set. Okay. And we suppose that D is a union, is the union of countably many disjoint open subset U sub I of right, so D is the union of countably many disjoint open subsets Ui of U such that for each I, the restriction G di of the vector value function G on di is a coordinate transformation. Okay, it's coordinate transformation on di. And the intersection of any subcollection of the ranges Gi and Ui's. Okay. Ui, sorry. It's Ui. And the intersection of any subcollection of the ranges of Gi is an open subset of Rn. Okay, so now the domain of this vector value function G is decomposed into open subsets Ui. Okay, and these Ui's are disjoint from each other. And if we restrict, sorry. And when we restrict the vector value function G to each Ui, then this restriction becomes to a coordinate transformation. So we call that G is piecewise a piecewise coordinate transformation. Okay. All right. So this is case, and now we let HI, okay, be the inverse transformation of the restriction G to UI on GUI. Okay? So each piece, right? Because when we restrict G to UI, it's a coordinate transformation. So it has inverse from mapping HI. So each HI is also a coordinate transformation on this open set G of UI. Okay, G of UI. Now, so this we will then Y1, which is G1, Y2, which is G2, Yn, which is Gn, right, are also jointly absolutely continuous. Okay? Random variables with joint PDF. Okay? The joint PDF will be which is equal to J F X H I Y Jacobian H I sub J and of Y. Okay. And J here. I sub J. And the Jacobian of G at H I sub J of Y. Okay, and take the F value for all point Y. Okay, for all point Y in GD, GU. Okay. And where I sub J are all indices such that Y is in G UI. UI sub J. Okay, it's in the UI sub J. Right, and the joint PDF of Y1 up to Yn is 0. Okay, for all Y is not in GU. Okay, so the statement is a little bit long. Okay. So because Y is in the range of G, right? And there are possible many X sub I's, Ij, such that, so you see that so that so given Y in the range of G, okay, they may possibly many X sub Ij in U I sub j in the component such that the G of X I sub j is equal to Y. Okay, right? Because the transformation G may not be one-to-one on U. Okay, so it may not be on. So it's possible for Y in the range that you may have more than one X point such that G of Xij is in Y. But we know that in each component of U, there is at most one X point such that its image is Y. Okay. Because restrict to this component, G is a coordinate transformation, so it's one-to-one. Okay. Right. So we have to account for this I sub j's, these indices. Okay. So that we have to sum over all possible such j with I sub j. Okay. Has this property. Okay. So you may think about that. This is actually equal to X I sub j here. Okay. So this one, this is X I sub j. Okay. So this is X I sub j. This is X I sub j. Okay. So that this is the evaluation we have. Right? And the proof is quite similar to the previous proposition. Okay, so right. So since the joint PDF of random vector x is 0 almost everywhere outside the open subset U of Rn. Okay, so we have probability that the one byte vector is in U is probability 1. And then we know that probability of y is in G of U. Okay, so any probability is upper bounded by 1. All right, so y is in G of U. Okay, so this is probability, but y we know is G of x in G of U. All right, and this is greater than or equal to probability that x is in U. Okay, and we know this is 1, right? So by sandwich property, this probability must be equal to 1. Okay, now we have to see why this is true. Since okay, when we have this event, okay, this event is contained in so whenever the random vector has value in U, then after the data processing, the vector data pattern of G, we know that it should be in G of U. Okay? Right. So this implies that, so this is bigger. Okay, this is bigger. All right. All right, so the probability of x in U would be less than equal to the probability that G of x contained in G of U. Okay, so it's here. So we have inequality. And so from here, we okay, so that's probability that y in G U is equal to 1. Okay, so we will focus on the range of G, right? G of U here. All right, so we consider a point y in G of U. Okay, and let I sub j be all indices. Okay, such that the y is in I sub j. So in the range of this piece on the G. Okay, U sub I. I.e. there X and X in such that Y is equal to G of J. Okay? So so we consider all the indices here. Okay. So then Y will be in the intersection of all this Ui sub J. Okay. All right. So we have take the intersection here, and by our assumption, since this intersection, so because we say that a subcollection, the intersection of any subcollection of GIUIs, okay, but GIUIs here, this one is equal to G of UI, the same. So since the intersection is an open set, so if an open subset of Rn, there is an open n-ball B, Y, R contained in the intersection of these ranges of these pieces. Okay. So now we compute probability of Y in the n-ball. Okay? Then in this open n-ball. And this is equal to probability that an X is in. So G of G of X is in the n-ball. Okay. And so this is equal to a probability that X is in the union of J of Hij of the ball. Okay, here. Okay, so the picture is here that we have I write here. So we can have, for example, a piece. So this is U. So for example, this is I1, U, I2. Okay, map 2 here. So okay, this is by UG. Okay, and we have that. So okay, so this is G U I1. This is G U I2, and this is G U I sub j, for example. So that we have the intersection here. Okay. And in this intersection, we have an open ball. So this is Y, and we take an open ball. So this is ball, Y, R. Okay. All right. So the intersection is open set. So there is open ball here contained in here. Now that so the correspondence so that in here, okay, we have xi2, we have xi1, we have xij. Okay, so all these points were mapped to y. Okay, so they all map to y. Okay, by G. Okay, by G there. Now, because that if we restrict G into each component, the G is a coordinate transformation. Okay, so that and because the open ball is in the range of each U sub ij, okay, so that the inverse mapping, okay, so we have 1 to 1, and here the inverse mapping, okay, so we go so we have the inverse mapping, the I1 from here to there. So this is HI1, okay, and let me take more colors. Okay, and this one, oh, this is U1, right? So U1 should go to here. And U2 should go to here. So this is HI2. And this one will go to HI sub j here. Okay. All right, and so that the inverse So the open ball in here, when mapped by HI1, you get here. So you have a subset. Okay, and this is subset. It's HI1 of Y. So you can see that X sub I1 is in here. Oh, I'm sorry. It's in HI1 of ball. Okay. And in here, we have another one. This is HI2 of the ball. Okay. And for here, we have HI sub j of ball here. Okay. So that the G of Y, okay, the mapping will go, right? So this event, okay, go to this open ball, right? If and only if that the random vector X is in each of this open set, okay? So it's in this region or in the red region, okay, in the red, or the yellow one, or the green one, okay. Okay, so this event occur if and only if this event occur. Okay. But as you can see, because U sub I, J, they are disjoint to each other. So this becomes to be a disjoint union. Okay? The disjoint union here. And so that, all right, so that because this is joint union, so we have the summation of J and probability that X is in H I sub J of ball Y R. Okay, it's in here. Okay. All right, and so now this is an event, okay, defined by random vector X. Okay, so we will do the integration in H I sub J B of Y R, okay, and F of the joint PDF dx. Come this one. Now we will do the change of variable, right? For each, okay, for each H sub ij, okay. So now, so this is become 2. by the change of variables. Okay, so that so x, so x is equal to h of ij u. Okay. Right? So that this is, because this is a coordinate transformation. Okay. This is a coordinate transformation here. Okay. So we use this coordinate, and then we have the change of variable. Okay. So this is from proposition. This one 7.8. Okay. Right. So we have that. All right. And now they have the common integration region. So this is U in the open ball, center at Y, and radius R, summation of J, F of Hi sub j, U, I sub j, U, du. Okay? All right. So we start from here. The random vector is in this open ball. Okay. And it's equal to that we integrate. So in this open ball and y. Okay. So where is defined to be summation of j f of x hi sub j u Jacobian hi sub j u here. Okay. For all u in what? In the GU. Okay, so we here. Okay, because that we define this for all u in the open ball of YR, but as we see that the open ball when Y is go around GU, okay, when Y is go around GU, then when Y is go around GU, okay, then this definition will be valid. So this is definition is only valid for all the U in the range of G. Okay, so we have that, and so from this y in here give us this one, right? So this shows that y1, y2 up to yn are jointly absolutely continuous with a joint PDF. Okay, with a joint PDF. With a joint PDF that fy into y is equal to summation j okay, and the 0 complement. Okay. Right. So this is the end of the proof. Okay. So, so this is the. I think this is the most general version to answer our questions raised at the beginning of this section. All right. So, so I will stop here, and we will omit section 6.8. Okay. Right. So that so we will have a second midterm next Thursday, and the coverage will be chapters 5 and 6.